Okay, today we're going to practice. We're going to work on the things we've been talking about the last couple units here, sections. And we got 4 practice questions. Okay, so atoms of magnesium. Whoops. There we go. And atoms of fluorine. So if we put those two together, magnesium is in the +2 column of the periodic table, and fluorine is in the -1. So that would mean you'd need 2 fluorines for every magnesium. Atoms of which the following elements combine with atoms of fluorine in the same ratio. So which ones would give you 1, we'll call it X, compared to 2 of the F's. So you'd need something in the same column of the periodic table to give you a +2. And the only one that's going to work with is barium. Barium is in the second column, the alkali earth metals. So it would combine in the same ratio. So these are all periodic table related questions. Which of the following elements has the largest first ionization energy, meaning it's the hardest to lose an electron? So metals are easy to lose electrons. So we're not going to like beryllium or lithium. We're going to like something further over left to right on the periodic table. And I don't think we're going to get a chance here, but we would also like something higher up on that right side. And so in the second column, you got boron, then you got carbon, then you have nitrogen. So you could memorize this as the answer nitrogen, but we're going to talk about why it is greater as you go left to right on the periodic table. So as you go left to right, boron has 5 protons, carbon has 6 protons, and nitrogen has 7 protons. So the nuclear pull, the Coulombic attraction, is greater. The Q here is greater for nitrogen than it is for carbon or boron. So that's how we got to answer E, nitrogen. Okay, electron configuration it looks like here. Which of the following is the electron configuration of excited? Okay, so excited doesn't mean ground state. It means electrons or electron further away from the nucleus because it has more energy. So let's see. Are there any that satisfy the octet rule but jump further out? 1s2, 2s2, 2p6, 3s2, 3p1, that's just ground state. So it's not A. A is off the board. 1s2, 2s2, 2p6, 3s2, 3p5, that's still ground state. So it's not B. 1s2, 2s2, 2p6, 3s2. Another one that's ground state, so it's not that one. 1s2, 2s2, 2p6, 3s1. Again, ground state. So process elimination, it's E, but why is it E? This electron in the 3p1 should be in the 3s. It should be 3s2. And then this 3p would be empty, but this electron possesses enough energy to jump out of that 3s suborbital into the 3p. Okay, and our last question, free response. So I would think this would be a typical kind of question that you could get on the test. For free response. This was from a previous AP question, AP test one year. Write the ground state electron configurations for the atom of the following. This one has 31 protons, 31 electrons. Why? Because its atomic number is 31. And then this one has 33 electrons. Now, it doesn't say write the complete ground state electron configuration, but we're going to do the complete. So we're going to start off-belt principle, 1s2, 2s2, 2p6. I'm going to put a little line there. This is how I kind of keep myself straight and not keep my counts right. I have 10 electrons. Then we go to 3s2, 3p6, 4s2, that's 20. Then we dip back to 3d, and remember the d's can hold 10. So I've accounted for 30 electrons, and then 4p1. Let me change the colors here for a second, show you something that you may or may not know, that depending on what column and what row the element is, in this case gallium, it's in the 1, 2, 3, 4, fourth, let me write this over here, fourth row, and it's in, I'm skipping the transition metals, but it's in the third column. So what does that mean? It should end in 4s, 4s and 3p, and then those ending the highest principal energy level, in this case 4, should have a total of 3 electrons. 2 plus 1 is 3. So you can kind of keep straight how far you should be going out by doing the row and column idea there. Okay, so now the next one, very similar, but it's just going to have a little bit of a different ending. I'll write the whole thing out. Let's give it another different color here. Let's go blue. So still 1s2. We're gonna basically go exactly the same, just go 2 more electrons past that. So instead of 4p1, we'll go 4p3. And then the same should apply that we talked about before, using the periodic table to kind of guide us. It should end in the 4th row, which it does, and then 2 plus 3 is 5, so it should be in the 5th column. Again, skipping the transition metals for counting those columns, and that should work out. B, let me move this up just a little bit. On the test, you'd have room to answer these, and I think I've given myself room down here to answer these also. But I'm gonna try to answer them here so we don't have to go back and forth. Okay, so we have the same 2 elements that we had previously. Lots of times, part A, you might need part A to do part B and so forth. I don't think that's going to be the case with this one, but first ionization energy, that means to lose 1 electron. And then this is to lose the 2nd electron. I'm just going to write it as another electron there. So explain in terms of atomic structure. So atomic structure, that's going to be dealing with protons. I don't think we're going to need to talk about neutrons for any of these questions. In electrons, we can also talk in terms of Coulombic attraction. Okay, so that's the Q's, the charges, nuclear pull, in this case the protons, and the R is the distance, well, the radius, but the distance from the outer electrons, because that's the ones you're going to lose first, and the nucleus. So why would it be harder to lose an arsenic electron compared to gallium? So first of all, let's make sure that that is the case. And it is the case, 950 is more than 580. Okay, so why would that be the case? So they're both in the same, let me move this down, move this. They're both in the same row, so it can't be about R, the distance. So it must be about the Q's. So arsenic has, again, 33 protons. It's the atomic number 33, and gallium has 31 electrons. So I don't really have enough room to write that right here, but I kind of just explained it. So arsenic has more nuclear pull, more Q, more Coulombic attraction to those outer electrons than gallium does. Okay, so now second, this kind of goes against what I just mentioned previously, but we're going to have to try to explain that. So why would gallium, why is it harder to lose the second electron? Well, if you remember, we had exceptions. I think we talked about boron versus beryllium and nitrogen versus oxygen, some exceptions to why it's easier or harder to lose electrons. And with gallium, it ends in, I'm just going to go back to the electron configurations here, it ends in 4s2, 4p1. I'm going to write gallium's orbital diagram here, the ending, and it looks like that. And then arsenic ends in 4s2. So here's that, and then 4p3. And if you remember, I was telling you that if you have a half-filled or filled orbital, it's very, very difficult, or more difficult, to lose an electron out of there. It's fairly stable to have half-filled and filled. But gallium, on the other hand, has this singleton electron in the p orbital there, and that's not very stable. It's fairly easy to lose that electron, for it to go bouncing away. So, although this question's about losing the second one. So, fairly easy to lose that one, but then it's in these s orbitals. So that's, again, I said half-filled and filled are more difficult. It might be kind of easy to lose that first one, but the second one here would be easy. But in this case, for gallium, it would be very difficult because it's a filled orbital there, the s orbital. So we're not going to try to go and use exceptions unless we have to. We'd much rather use this Coulombic attraction idea with protons and distance from the nucleus. But if you are presented with data that suggests otherwise from our trends, then you have to use these exception ideas. So AP knows that all the AP teachers talk about boron and beryllium and nitrogen and oxygen, but they threw this new one at us here, this gallium and arsenic. So they're always going to try to give you a little bit of a different angle here for these questions. I'm going to try to erase some of these things here because we're not going to have enough room to do part C here. And we'll also, after we're done here, look at the AP answers. It'll be on the next slide. Okay, so now we have an ion. So what is an ion? It's going to have a charge because it's gained or lost electrons. This one has a +1, so that means it still has the 31 protons because it's the atomic number 31, but now it only has 30 electrons. Let's see, identify an ion of arsenic that would be isoelectronic. That means it has to have 30 electrons for gallium +1. So normally arsenic has 33 electrons. Well, we need it to have 30. That means it has to lose 3 electrons. So if you have this, that would work. Okay, which species has the largest radii? Gallium ions or the one we just used, arsenic +3. So size deals with charge, and it also deals with distance away from the nucleus. Well, if they're isoelectronic, it can't be about the distance because they're going to have identical distances from the nucleus. So now it's about charge. And you have 33 protons for arsenic. And I'll write this over here. Actually, I'll just do that. 31 protons for gallium. So arsenic has greater nuclear pull, so it should be able to bring those electrons in a little bit closer. Gallium, on the other hand, only has 31, so it should be a little bit bigger. So which one has the largest radii? It would be gallium, and again, it's because of that Q, 33 protons versus 31 protons, or I should say 31 protons versus 33 protons. But let's go check out their answers and see if they, by the way, these are just for me to, I could have put my work there. So here is the electron configuration, but this is a little bit different here. This is a shortcut, and it doesn't say the word complete ground state electron configuration. So if it doesn't say complete, you can do this shortcut, and the shortcut would be going to the previous noble gas, so one row up, and in this case it's argon, and then all the electron configuration after argon. So argon is the 1s2, 2s2, 2p6, 3s2, 3p6. I know this is small here, but that's the argon part of the electron configuration, and then you just need the rest of it. And then arsenic, they do the same thing. They go here, arsenic, and then everything after. Okay, let's take a look at their explanations. Why does arsenic have a higher first ionization energy? And it says about the nucleus having more protons. And that, I think we used that same idea. They didn't use Coulombic attraction by name. They didn't even use the Q1, Q2 divided by R squared idea. But it looked like the graders suggested that if you just used the more nuclear pull because more protons, that would have worked. And then second ionization energy, it talks about 4s lower in energy compared to remove an electron from 4p. It doesn't talk about full, half, empty like we were mentioning. I think I would have suggested that all my students add that in there, but they were okay this particular year without that explanation. But every year, these AP graders, they collectively figure out what they're going to accept and not accept. And just because they accepted it this particular year doesn't mean they're going to accept it the following year. It's a different set of graders. So I would think you might want to use that that complete or full, or it didn't come up with this question, but that half filled idea. So if you have a half filled like P grouping there, that's fairly stable and it's hard to lose an electron out of there. Or if you have a filled like s orbital, that's hard to lose an electron out of there also. That's more stable. Okay, I think we have a little bit more explanation here. So I think that matches up with what we said. Arsenic +3 would have the same number of electrons as gallium +1, and which would be larger, and it talks about protons. And so they didn't mention Coulombic attraction, whoops, R squared. But I think it would be nice to actually mention the nuclear pull being greater, but they just mentioned protons. Okay, and I think that is all we got.